Welcome, everyone. This lecture is about t-tests. I'll do my best to keep it concise. If you did the reading, you'll understand the interesting story of the history behind how the t-test was developed by this guy, William Gossett, while he was working at a Guinness factory. Some interesting stuff. But anyway, let's go ahead and jump right on into the lecture. So we're talking about single sample t-tests. Some people call it a one sample t-test. And the purpose is to compare a sample mean to a known value or the population mean. In other words, we're comparing the average or the mean of your sample, which is the data that you collect, the observed data, to the average of a population, which is, what is expected or some known value. Also, I forgot to mention, for t-test, you'll need page 3 of the formula document that is on iCollege. All right, so our statistic for t-test is T. I wanted to start off by breaking down this formula so that when we get to that step, you'll be prepared. So this is the formula for T. It's mean minus mu over SD sub M. So these are the parts. So M is for mean. That is the sample mean, the mean for the data that you collect. And then mu, that's this Greek letter here that looks like a little u, is actually called mu. And that is the mean for the population or the known value that you're comparing your data to. And our denominator, which is SD sub M, which is the standard error. Standard error is the natural discrepancy that's going to occur between a sample statistic and the corresponding population parameter. There's always room for error in statistics, and this is how we control for that, by dividing by this standard error. So you'll always be given the mu or the population mean because, again, that is a known value. And most times you'll be given the sample mean as well, so M, or if not, you know how to calculate the mean. So that's not difficult. What we don't know yet is how to calculate this standard error. So let's talk about that. So here is the formula for standard error. It is the square root of SD squared, which we know is variance, divided by n, which we know is our sample size. So how many subjects are in the data that we've collected. So there's still some unknowns in this formula. We'll probably likely be given n. We will know the sample size, but we do need to calculate the variance, so SD squared. And luckily, we've already learned how to do that this semester, right? So the formula for variance is sum of squares, or SS, over or divided by DF, which is our degrees of freedom. And in this case, our degrees of freedom is equal to n minus 1. So this is all the information that we're going to need when we get ready to actually solve for T. So here again is the overview of the hypothesis testing steps. Step 1, we're going to state the hypotheses. And for t-test, you need to figure out if it's one-tailed or two-tailed. We need to know the direction of the hypotheses. Step 2, set a criteria. Step 3, get our data and compute our sample statistic, in this case T. And then step 4, make a decision. All right, so there's two possibilities for the t-test hypothesis. They can be non-directional or directional. And the first step is to figure out which one it is. This is really important because it helps us in the next step when we set our criteria. So if it's non-directional, then you have a two-tailed hypothesis. This just means that you don't know which direction the difference might be. So the null hypothesis is going to be that there's no difference between the sample mean and the population. And then the alternative hypothesis is that there is a difference. They're not the same. The sample mean does not equal the population mean. But we don't specify if the sample mean is going to be higher or lower than the population mean. We're just testing to see if they're different at all. So if you're reading a test question or a problem and the setup doesn't mention if the researcher expects or hypothesizes a specific outcome, then the hypothesis is two-tailed or non-directional. The sample mean could be higher or could be lower. Your t-test could have a positive or negative value. We don't know. We just suspect that there's going to be a difference. A directional hypothesis means that the researcher is more specific about the difference that they expect. They hypothesize or predict that their sample mean from the data that they collect will either be higher or lower, depending on what they think, than the population mean. In either case, the null hypothesis is going to be the opposite of that. So if the researcher thinks that their sample mean is going to be higher, then the null hypothesis is that it'll be lower or equal to the population mean. And if the researcher predicts that their sample mean will be lower than the population mean, then the null hypothesis is that the sample mean is going to be higher than or equal to the population mean. So basically, the null hypothesis is the opposite of what the researcher predicts, including the possibility that there is no difference between the sample mean and the population mean. The alternative hypothesis is obviously whatever the researcher actually predicts. So if they predict that it's higher, then you expect the t-test to be positive. The t will be a positive value. And if they predict that it's lower, then you expect the t-test to have a negative value. Okay, so let's look at this example. A math professor wants to know if the students in her class have a good grasp of basic math compared to the general population of math students at the school. So this professor wants to compare a sample of students in her class, that's going to be her observed data, to the population of students at the school. 6 students are chosen at random from her class and given a math proficiency test. The professor predicts that the sample mean will be above the population mean, which is 70. So the 6 students in her sample get scores of 62, 92, 75, 68, 83, and 95. Did this sample score significantly higher than the general population? We're going to use an alpha of 0.10 or 0.10. So the first thing we want to do before we move forward is to take inventory of all the information that you have. If you're taking notes, I would recommend making a list off to the side to reference easily. So we're going to make a list of all the information that we have. So what do we have? We have the sample size. We know that n equals 6. There's 6 students in the sample. We also see that the professor predicts that the sample mean will be above the population mean. So we know the direction. This indicates a specific direction. So this is going to be a one-tailed test. We expect it to be positive because she expects that it will be higher above the mean. We also know the population mean, or the mu, is equal to 70. So the general population of students at the school as a whole have a mean score of 70. And I have the data from the sample here, so I can easily calculate the sample mean, or m, by just adding all of those values and dividing by 6. So you can pause to do that if you want, or here's the answer. So the mean is 79.17. So the professor's class has an average of 79.17, and the school's average, the general population, is 70. At face value, the professor's class has a higher score, but we need to do a t-test to see if that difference is statistically significant. And finally, I see that I have an alpha of 0.10, or a significance level of 10%. And I'll make sure to note this because it's different from our usual of 0.05. It's actually less conservative than 0.05 because this is 10%. So we're giving up ourselves 90% confidence range instead of 95%. Okay, so this is all the information that we need going forward. So step 1, we state the hypotheses. We've established already that this is a one-tailed test. Again, we know that because the professor stated a specific direction. And he thinks that the class is going to score higher than the population mean. So that's the alternative hypothesis. The null hypothesis is the opposite of that, while including the possibility that there's no difference. So the null hypothesis is that the mean scores of the students in the class will be less than or equal to the mean of the scores in the general population of the school. Next step is to set our criteria. We're going to use this chart, which again is in your formula packet on page 3. So here's the information we need to know in order to read this chart. We need to know if it's one-tailed or two-tailed. We've already established that it's one-tailed. We also need to know the degrees of freedom. In this case, degrees of freedom, the formula is n minus 1. N is our sample size, which we know is 6 students. So I'm just going to plug that in. df equals 6 minus 1, which is 5. So you can add this information to your list of info. df equals 5. I can find that on the chart too. And lastly, we need to know the alpha or the significance level, which we already know is 10% or 0.10. Make sure you don't confuse this with 0.01. So 0.10. So we locate that information in the chart and we get a criteria of 1.476 or 1.48 when we round to the nearest hundredths place. So we can also add this to our list of information. Our critical value is 1.48. We know that it's positive because that's what we're hypothesizing. All right, so here's our data, all of our scores, and we also have our mean. And here's our formula for t-test. Again, in order to solve this, we need to figure out our standard error. In order to figure out the standard error, we need to solve for the variance. So in order to solve for the variance, we need to know the sum of squares, which we don't have that yet. So we need to calculate for sum of squares first. And usually for the test and for other problems, I'm going to just give you the sum of squares. You already have this information because this is a lengthy process, but I want to show you all of the parts of that go into solving for t. So you can pause if you want to calculate the sum of squares, and I'll just display the answers and talk through it. So we already know the sum of squares formula is this right here. We're going to take each deviation, square them, and then add it all up. So here are the deviations. That's each score minus the mean. And then here are all of those values squared. So I just multiplied each of them by themselves. And then the last step is to get the sum of all those values in the last column. So when I add all of that, here's the sum for all of those values. So our sum of squares equals 866.84. And we already know that our degrees of freedom equals 5. So we're just going to plug that into our equation for variance. To find variance, we divide 866.84 divided by 5, and we'll get this answer. And again, I'll remind you, I'm walking through this, just going through it, but make sure that you're pressing pause while you're watching to do these calculations on your own, and then double check your work. All right, so our variance is 173.37. Now we're ready to calculate the standard error, and we just have to simply plug it into our equation here. So we know that our sample size is 6 students, so we're getting the square root of 173.37 divided by 6. So if we do what's under that square root, we have 28.9, and the square root of that is 5.38. So now we are finally ready to solve for t. And if we look at our list of information, we have everything we need. We just need to plug it into the equation. So here we do that. We have the mean minus the population mean over the standard error. So that's our numerator is going to be 9.17. We divide those numbers and we get 1.70. So that's our t. Okay, so we made it to the last step, which is to make a decision. We'll compare our t statistic that we just calculated to our critical value, which we got a little earlier. And if our t statistic is greater than the critical value, we can reject the null, and our result is significant. If the t statistic is less than or equal to the critical value, we retain the null, and our result will be, we can conclude that a result is not significant. So our critical value, if you remember, was 1.48, and our t statistic is 1.7. 1.7 is greater than 1.48, so we can reject the null. Our conclusion is that our result is statistically significant. And so the way that I can interpret that in the context of the original problem is that the students in the professor's class score significantly higher than the population, which is the rest of the school. All right, awesome. So here is something to think about. What if we had set our criteria at 0.05, which is 5%, instead of 0.1, which was 10%? So here's our chart that we used originally. Based on our significant level that we had, which was 0.10, our critical value was 1.48. So if we set our criteria at 0.05, which is a more strict criteria, we would have a critical value of 2.015 or 2.02. So remember that our t-value was 1.7. So if we were to set our criteria at 0.05, we would have to retain the null hypothesis. Our result would not be statistically significant. And I just wanted to show you this to illustrate that the criteria really matters because it determines what kind of interpretation you can make about your results. All right, so here is workshop number 10. This is the last workshop of the semester. And even if you don't plan to submit this for credit, you should still be taking some time to complete it for extra practice because you will see something very similar on the exam. So I'm gonna read through this and kind of get you started, walk through some of the steps here to help you out. So a psychologist has prepared an optimism test that is administered yearly to graduating college seniors. The test measures how each graduating class feels about its future. The higher the score, the more optimistic the class. The psychologist wants to compare last year's class to this year's class to see if there is any difference. Last year's class has a mean score of mu equals 15. A sample of 9 seniors from this year's class was selected and tested. They had a mean score of m equals 10 with a sum of squares equals 94. Is this year's class significantly different? So we're going to use alpha equals 0.05. So this is a similar setup here. The psychologist is comparing a sample from this year to their known value of the mean from last year. So again, I just want to highlight all of the information that we already have, and you can make your list of information again. We've got our population mean, which is mu equals 15. And we also have our sample size, which is n. So there's 9 students, 9 seniors from this class. And they had a mean of 10. So the mean score is 10. And then another piece of information we have here is the sum of squares. So we don't have to actually calculate that this time. And we have our significance level of 0.05. And so here are the questions which basically walk you through the steps. The first is to figure out, is this one-tailed or two-tailed? So we see here that the psychologist wants to compare last year's class to this year's class to see if there is any difference. There's no specific hypothesis specified. The psychologist just wants to see if there's a difference. So that should tell you that this is two-tailed. Okay, this gets you a step closer to finding the critical value, which is number 2 on this list. So we know that it's two-tailed, and we know the significance level is 0.05. We still need to know the degrees of freedom, or DF. We know that DF is n minus 1. Sorry, that should say n minus 1, not n equals 1. So our n is 9. We just plug that in. So 9 minus 1 is 8. So our degrees of freedom equals 8. So we have that information. We can use that in the chart to find the critical value. And then on to step 3. First, you're going to find the variance. So here's the formula for variance. We already know sum of squares. That was given to us in the problem. So we just plug that in. We already know degrees of freedom. And then once you solve for that variance, you'll be able to calculate the standard error. So you plug in your variance, and then you know that the denominator there is going to be 9 because we have a sample size of 9. And then once you get that, you'll be ready for number 5, which is to calculate the t-statistic. And finally, once you get the t-statistic, you'll be ready to make a conclusion by comparing the t-statistic to the critical value and deciding whether to reject or retain the null hypothesis. All right, that's it for today. Hope you have a good day, and definitely email me if you have any questions. All right, everybody, take care.